So our next talk is going to be by Kinjal Basu on large-scale QCOP via low discrepancy sequences, joint work with Ankan Saha and Shaunak Chatterjee.
Thank you for the introduction. So this has been a work in the making for quite some time, and it's been joint work with my colleagues Ankan and Shaunak. So large-scale QCOP stands for this class of problems known as quadratically constrained quadratic problems, where it's a major class of problems and it's thought to be quite hard because in the very general setup it is NP hard. But to begin the talk, I just want to give some brief motivation of how do we arise with such problems in practice. So if you think about it, one of the major problems in most social media is feed ranking. Whether it be at LinkedIn, Instagram, Facebook, and so on and so forth, feed ranking is a very challenging problem. And such similar ranking problems also come up in several other applications. For example, if you consider people you may know, then it's a list of members who you do not know but want to connect to. So this kind of ranking problems is kind of in the similar nature. Another very common example is the set of notifications. So you have a group of notifications that you want to rank, and how do you actually rank them appropriately so that certain metrics you can raise and certain metrics you can decrease. So any kind of ranking problem actually tries to optimize over a range of multi-objective metrics. So for example, if you consider the feed example, you would want to increase engagement by showing things which are very appropriate to the user, but at the same time, you would not want to drop revenue. So if you do not show too many ads, the revenue will drop. So how do you actually create this ranking system so that there is a delicate balance between these metrics? And the major problem that happens is that these metrics, if one decreases, the other tries to increase, and so on and so forth. So the major example that I'll continue through for most of the talk will be on notifications. So if you consider the domain of notifications or emails, the major problem tries to factor in that we will not try to increase too many sends. So we'll try to decrease the number of sends that we can, but at the same time, we do not want to drop sessions. So we know that if, in the case, especially in the short term, if you send too many notifications, the user will come and visit your site more often, but that hampers the user experience. So what we try to do is we try to decrease the total number of sends, but at the same time, do not want to drop sessions. So if we want to solve this kind of a problem and do the ranking, how do we actually go about it? So this is how we try to formalize this optimization problem. So consider the problem that we are solving is minimizing sends while the sessions do not drop. So I'll talk a little bit about the notations which will help in the rest of the talk. So, okay, this doesn't work. So Xij, consider that to be the probability of sending a particular item j to a user I, okay? And let Qij be the prior probability of sending it. Like beforehand, you used to send those particular notifications with that probability to the user I. And Sij be the probability that this user will visit given an item j is sent to this user I. So if we want to write this out as a proper optimization framework, what we do is we try to minimize the first term, which is basically the total expected sends. And the second term is kind of a regularizer, which tries to incorporate the fact that we are not swaying too far away from the previous prior. And the constraint that we have is that the expected sessions, that is sum over Xij, Sij, is greater than some threshold. Now this threshold can be given by product or can be appropriately judged from problem to problem. And the last factor basically tries to account that Xij is a probability. So if you solve this problem, then we will get Xij, which will basically tell us, okay, send this notification to user I or send this email to user I, but do not send the other. So far, this problem is basically a QP. So we see that it's a quadratic objective with linear constraints. So far we are good. So how do we actually get or come to a QCQP? So the way we derive it is as follows. Now the probability of this Sij that a person visits given that you have sent him a particular notification depends not only on that particular notification, but also on things that you have sent in the past. For example, till the last sends, you have not sent him too many flashy pushes, or you have sent him multiple flashy pushes that makes him come back. or you have kept badging the person over and over again, so the badge count increases, and after like 40 odd badges, he says, okay, finally I've come in. But so if you want to keep this framework within it, what you need to do is you need to write down the total number of sessions, that is Sij, as a function of your variable x. Now, as soon as you do that, for example, if you write this as a linear function, here S is just a vectorized version of your Sijs, then you can write it as a matrix P times your variable of interest x. So if we just try to parse this for a second, if you just consider a particular Sij, then it's a linear combination of all the things that are sent to you. So it's xi1 to xij times certain latent factors. And these latent factors can be learned from one problem to the other. So if we actually do this kind of a proper modeling in this setup, what happens? So this was our initial problem, which was minimizing sends such that the sessions do not drop. Now the derived problem becomes, so I'm just writing it in a vectorized form, so it's x transpose 1, which is exactly that, plus the second order term, subject to now the constraint that x transpose px is greater than c. So from a QP, we have derived or come across a problem which is QCQP. Now this problem in general becomes extremely hard to solve. So what do we do about it? So the main overview that I'm going to talk about are the 4 things, that what are the current challenges about solving these kind of problems, what is the technique that we have developed, some theoretical guarantees on that technique, and finally I'll talk a little bit about some of the empirical validation. So as I mentioned before, that the main challenges of solving a QCQP is the fact that in the very general setup it is NP hard. And that's very easy to see because any 0-1 integer programming problem can be converted into a QCQP. And that is known to be NP hard. So the usual solutions that are there, and I think the other speaker mentioned it before, is that we convert it into a semi-definite programming. Or there's another relaxation technique, which is known as the linearization technique. But in both cases, what happens is that even if the initial problem had a dimension of n, the transferred problem in the SDP relaxation or the RLT relaxation becomes order of n square. And in the ranges that we are talking about, where x can be in the range of hundreds and millions, this is just infeasible. We cannot do this. So what do we do? So the main idea comes back to the fact that we were solving a large-scale QP for a long time. And there are very, very good state-of-the-art methods that can solve it, especially things like ADMM, Douglas-Radford, and so on and so forth. So the main idea is, can we somehow translate this QCQP back to a QP? So how do we do that? So imagine we have this original problem. So I'm framing it a slightly different way for easier experience. So imagine we have something like this, where it's a quadratic objective, very simple, and it's subject to this constraint that it's a quadratic constraint. Now what we are trying to do is as follows. This quadratic constraint can be seen as an ellipsoid of this form. So all that we are trying to do is we're trying to linearize it. The way we do it is by drawing tangent planes across, by choosing some points on the surface of this ellipsoid. So just by doing that, if we choose, say, 6 points here, what we get is the derived problem now becomes a QP, where we are replaced in the quadratic x by xj for j equal to 1 to n. So for n different linear constraints, we have now derived a QP from the QCQP. Now, if we look at it closely, given a particular n, the accuracy of this problem solely depends on your choice of n. So our choice of the n points, x1 to xn. So what do we do? So first choice, why not choose just random points? Well, random points do not work. It might work in some cases, in which case we are very lucky, but in most cases it does not. For example, what we are trying to do is trying to approximate this ellipsoid to the best that we can. But imagine instead, for a point that was there previously called x6, we don't have it, and we just have 5 points. The hyperplanes here go way, way beyond. So we are getting a very bad approximation. And in some cases, what can happen is that if this x5 did not exist, we'd get an unbounded set. And that can give to drastically bad results. So what do we do? So what we do is come up with something which was there in literature for a long time. It's known as some equidistributed points or low discrepancy points. So these are point sets which are very well distributed on the unit square, for example. And this can be generated in very, very high dimensions very easily. So it has the property that if you break this down, if you consider an n-point set, and if you break this square down into n smaller squares, each of them will contain 1 point. And that's the kind of equidistribution property that these points have. What that guarantees is that now if we map these points to the surface of a sphere and then map it again to the surface of an ellipsoid, we'll never ever get such large random gaps which was there previously present. So this kind of solves that problem. And that's the main takeaway from this talk. What we were able to show is the following, that if xn star denotes the optimal solution to the problem and x star is the true solution, then as the number of points go to infinity, that the points converge to the true solution. Moreover, we can show some finite sample results where f of x converges to the true solution f of x star and at the same particular rate. And this rate can be identified from problem to problems. So finally, I just want to give a brief example of an empirical study that we did. So we considered some problems which were very high dimensions, going from 5 to 1 in a million. So what we did was, we know that if the global objective has the true solution within the constraint set, then we are fine whatever points we choose, because it's anyways covers the set. So we actually created an artificial set where the global objective has a global minima which lies outside the constraint set, and as a result, the solution will be on the boundary point of the constraint set. So if we do that, and we solve it for, just look at the first row, then the exact method is solved by the interior point method, and SDP and RLT are the two relaxation techniques, and they are very close to each other. The best that we can get for our approximation is a value of 3. So it was a minimization problem, so we did not get something in the true feasible set, but we are not that far. However, if we choose a different kind of sampling scheme, for example, if we choose random uniform sampling on the hypersquare or random uniform sampling on the sphere and use the same mapping transformation into the ellipsoid, we get much, much worse results. We get results which is approximately, if you look at the row with 50, of objective value of 15,000, where the truth is 1.11 to the 10 to the power of 5. So it can be really, really bad in certain situations. So lastly, I just want to say that we can show that if we plot the relative squared error, because we know the truth in certain small dimensions, our model does in logarithmic terms much better than the other simple simulation schemes. So finally, I just want to briefly talk about some of the future work that's going to be done. So we want to compare this with various commercially available solvers like Simplex, or with large-scale SDP solvers such as ADMM. These are hard things to do in practice, but we want to do that. And on a theoretical point of view, we want to solve and give explicit small sample bounds for some of the common domains. And finally, we want to say that the exact rate can be found out by by kind of analyzing how the eigenvalues grow of the matrices that we are involved with. So for the summary and takeaway, we have a method that can solve, give a solution or an approximate solution to a QCQP problem with a theoretical guarantee. And rather than using random points, it's much better to use these low discrepancy point sets. And this can be used in several applications for feed, notification, email, and so on and so forth, which were previously blocked because of the scale. So that's all, and thank you for the attention.
Thanks, Kinjal. We have time for a couple questions.
Very interesting work, but I came from graphics, so we use LDS quite a bit. But using like Horton 1, Radix 2, 3 for your or each.
That was a TMS net.
That's TMS net, right?
Yes.
Okay. Yeah, that's what I thought.
Yeah.
Because otherwise you still get clumping. But one other thing that you might, there's a thing called spherical Fibonacci lattice that actually might be useful for you.
Yeah. So we can also so this was just one mapping where we wanted to create points on the sphere. But a Fibonacci lattice kind of is very hard to determine in especially very, very high dimensions. A TMS net can be automatically generated in very high dimensions. Yeah.
Any other questions? All right, great. Let's thank the speaker again, and we'll make the switch.